Hello and welcome to today's webinar, Simulation within Inventor Professional Part 2. This webinar is brought to you by Live Lab Learning, which is a subsidiary of Academic Corp, a wholly owned applied software company created to provide world-class training. My name is Patrick Muse and I'm delighted to be your operator today, or your moderator today. Throughout our presentation, we encourage you to interact with us by typing in questions and comments using the questions pane. We will be answering questions at the end of the presentation. This webinar is being recorded and will be available to you online on our YouTube channel. If you don't mind, please take notes of our upcoming events. And again, those are listed on the Live Lab Learning website at the bottom there. We do have a few extra ones coming up for the month of March. The Benefits of Bluebeam on the 3rd, Camelot with Inventor on the 10th, and then our final series of this three-part series, Frame Analysis Simulation within Inventor Professional on the 12th. And of course, you're more than welcome to contact me at that information listed, either by email or phone number would be great. I'm sorry about that. We actually have a couple extra ones as well. We have one in Atlanta on the 25th, and then one in Leeds, Alabama on the 26th as well. And again, you're more than welcome to contact me if you have any questions about that. Today we have Jason Miles, who is our Senior Application Manager. Due to his in-depth knowledge with this information, we decided to make this a three-part series, so this is obviously part 2. The first portion was already covered and it's listed on our YouTube channel. And we have the one that's coming up at the end of March, finishing with the series on the 12th. We just really wanted to make sure everybody was comfortable and had enough time to fully understand and utilize their software. So without further ado, please join me in welcoming Jason Miles.
All right, thank you, Patrick. I hope everybody's doing well today. So what we're going to end up doing today is we're going to simulate and analyze the dynamic characteristics of an assembly in motion under various load conditions. So let's go ahead and jump into our Inventor software. So there's a couple things that I'm going to end up talking about today. More or less our objectives are we're going to recognize the differences between the dynamic simulation application and the regular assembly environment, see how the software automatically converts mate assembly constraints to dynamic simulation standard joints. We'll use some color mobile groups to distinguish component relationships and manually create rolling 2D contact and spring joint types. And then we'll continue on and define some joint properties, and then we'll impose motion on a joint and define gravity. We'll get into a little bit about the output grapher, and then of course we'll run the dynamic simulation to see how joints, loads, and component structures interact as a moving dynamic mechanism. So the first thing you see here that I have open, we have a reciprocating saw. So here I want to talk about a few things here before we get into the dynamic environment. So one key thing here is to talk about the degrees of freedom. So in dynamic simulation, unconstrained and ungrounded components have 0 degrees of freedom and will not move in a simulation. So the addition of joints creates the degrees of freedom. When entering the dynamic simulation, components that have mate constraints receive these joints automatically. So whether either dynamic simulation or in the assembly environment, the main intent is to build a functional mechanism. So dynamic simulation adds to that functional mechanism the dynamic real-world influence of various kinds of loads to create a true kinematic chain. So we'll see here, I'm going to go up to my Environments tab, and we're going to start the dynamic simulation environment. Okay. So you'll notice right now I'm in the dynamic simulation environment over here in my model browser. And you'll notice that we have different types of groups. Okay. So we'll have such things as mobile groups. We have grounded groups here. So I just go ahead and minimize some of these. So the grounded folder, components with no degrees of freedom, that's what's going to be listed underneath grounded. Just like if we were in assembly, things that are fully grounded. We got some mobile groups. These are components with degrees of freedom, allowing them to participate in the simulation when forces are applied. So you'll notice I have a cam, crank here. We got our motor, and then we have a welded group. Okay. So if we come in here, and I want to go ahead and start applying some assembly constraints. So let's see what I can move so far. So I'll come in here on these bevel gears. Notice that I have those degrees of freedom. Okay, here on my follower, I got some degrees of freedom here, and then also here on my cam. Notice I can rotate that as well. Now, as of right now, you'll notice I have a simulation player. So if I hit play, notice we don't see any kind of movement at all. That's because I haven't added those joints yet. Okay. And then another thing, if you notice whenever I hit play, notice how everything over here in my model browser turns gray. Okay. And the status slider on the simulation panel moves. Okay, but nothing happens. Okay. This is just because we don't have the needed input as of yet. So the first thing that I want to do is I want to start adding some more joints to control the movement of my model. So I need to build those relationships between my two bevel gears. So if I come over here and look at, let's say in my mobile groups, let's say underneath motor or our motor component and then bevel gear. I'm going to right click on this and I'm going to choose edit. And the reason I'm doing this is I actually know that I have a surface in here that I can use moving forward and setting this up. So I know I have a cone surface in here that we're going to utilize. Okay, so once we have that done, now I'm going to actually go up and we're going to insert a joint. Now the type of joint that I'm wanting to add is actually going to be a rolling joint, and it's going to be cone to cone, or cone on cone. So next is, notice I need to make two selections. So I'm going to choose that face or that edge of that cone. Then I'm going to go ahead and move over and select one of the teeth on this gear over here. Okay, so now I'm going to have that relationship. Now we're going to see what happens whenever I move this bevel gear here to see if we actually have that relationship happening. So notice that we have both gears moving. All right, so what I'm going to go ahead and do is I'm going to go ahead and turn off the visibility of that cone that we just turned on. We'll let it catch up for a second. There we go. Okay, the next step is we want to continue adding our relationships. So the next relationship that needs to be built is one between the cam follower, roller, and the cam component. So this component here, and then our cam. So more or less, I need to make sure that this roller contacts this cam. Now, retaining degrees of freedom. So I want to retain the degrees of freedom of this follower. So it is a symmetrical part, and by default, dynamic simulation attempts to reduce symmetrical component movement. And you're probably asking why. So let me give you an example. So I want you to consider a wheel assembly. You have a tire mounted to a rim. That assembly is attached to the vehicle with lug nuts. The function of a lug nut for simulation purposes isn't to revolve around its axis. It is to constrain the assembly to the vehicle. So because the lug nut is a symmetrical component, the rotational degree of freedom is automatically removed. So this simplifies the model for simulation purposes. So if you want to retain the lug nuts rotational degrees of freedom, you can do so using the retain degree of freedom command. And the same is true in reverse. That is, you can use ignore degrees of freedom to restrict the degrees of freedom of a component. So to ensure that the follower roller contacts the cam while also keeping its degrees of freedom, we're going to have to do a couple things here. So over here in the mobile groups, I want to come down here to where I have a welded group. Okay, you notice I have two components, the follower and the follower roller. So on the roller, I want it to retain those degrees of freedom about that axis. So notice I'm just right-clicking and retain degrees of freedom. Okay, so that makes where the roller retains its motion characteristics. Okay, so now the next step was I need to make sure that this roller contacts this cam. So I'm going to go and we're going to insert a joint. For this one, on the type, I'm going to select 2D contact. Okay, so I just need to pick the two instances here. So I'm going to select this loop. And notice that for the Inventor users out there, notice that that's a visible sketch. I can actually utilize sketches as well. So that's going to be my second loop. All right, now let's go ahead and say OK there. So next, we want to drag this follower just a little bit. And if you notice, it's not going through my part. It's actually touching it and running around the outside edge. So the 2D contact established a mechanical relationship between these two components. So before I go any further, I need to actually modify the properties of the 2D contact and display the force vector. So we'll notice over here, I've got a contact joints now. So I'm just going to go in and we're going to modify some of the properties. So here, a few things that I know that I need to set up, like in the parameters for restitution, we'll modify those just a little bit. And then the friction, that'll work good, 0.15. Down here at the bottom, I'm going to make the display force normal, and I'm going to set that scale, let's say to 0.003. Okay, so I have those set up. The next thing that I need to do, this follower is designed to slide through a portion of the guide component, which you see here. However, to hold this follower roller against the cam, you'll notice over here, I need to actually specify a spring between the follower and the guide components. So the good thing is that dynamic simulation offers a joint for doing that and more, and that is actually called the spring, damper, and jack point. All right, so this is really neat how this works. So I'm going to go in and we're going to insert a joint. And notice I'm going to come down here to the joint type, spring, damper, and jack. And you'll see the preview that I get here. So the first point that I'm going to actually select is actually on my guide where this follower passes through. So more or less I'm picking where this spring is going to be located. So I'll choose that. All right, so once I have that, we're just going to hit OK. So notice I get a preview of a spring here. Okay, but we need to actually go in because as of right now, we got a graphic representation of a spring, but the representation is deformable and has action, reaction forces, but it does not have mass. Okay, so I'm going to come over here. Notice now we have a force joints. Here's my spring. Come in here and modify some of these properties. So for this, I'm going to set the stiffness to maybe 2.5. And let's say the free length here, I'm going to make that somewhere around 42. And then down here at the bottom, say for the radius 5.2 turns, let's make it have 10 turns. And you'll notice that it's updating over here in my graphics window. And let's say the radius of our wire, I want to make that somewhere around 0.8. Okay, so once I have all those set up, let's go ahead and accept those. And notice we have our spring here. The next step is I actually need to come in here and I need to define, notice I have an external loads. I need to define our gravity. Okay. So here, let's go ahead and define gravity. And I'm just going to place that somewhere down here at the bottom. So that's where I'm going to define it. Alright, so really the direction, you want to note that the direction of the gravity has nothing to do with any external notion of up or down, but is set accordingly to the vector that I specify. Okay, so since we're using a reciprocating saw, I need to simulate saw operation. So it's necessary for me to impose motion. So in this case, I'm going to apply motion to the motor, just as we would in the real world case scenario. So to be able to do this, I'm going to have to edit some joint properties. Okay, so I'm going to come over here to some of my standard joints, and let's look at this revolution 2. Okay, that's my saw layout and my motor. So I'm going to edit some properties here. So in here, I can control, like for this degrees of freedom here, I'm going to actually impose motion. And I'm going to enable it. All right, but here I want it to actually be a constant value. All right, so with that, let's say 10,000 should do good for this. 10,000. All right, so once we have that, we'll say OK. Now the next thing is, because this simulation is of a high-speed device, I'm going to need to modify some of the simulation properties, and that's where the simulation player comes in effect. So notice the different input windows that I have here. I got final time, and then we have images. All right, so I'm going to do something along the lines of maybe 0.5, and that should be sufficient to demonstrate this mechanism. Okay, the next, in the images field, I'm going to add something like 200. Okay, so increasing the image count improves the results we will view in the output grapher. So that's why I said it's 200. Now, I'm going to see if I can move this up out of the way just a little bit. And we're going to play this. And I'm hoping, since we're going through the internet here, I'm hoping that it's not too choppy for you. So I'm going to hit play. And notice that we have our motor running, the bevel gears are turning, the cam, and also our follower and our follower roller is doing just as I set it up. We'll play it one more time. Okay. So as the motor component drives the bevel gears, you notice that the remaining parts in the kinematic chain respond. Also, because we have not yet specified any frictional or damping forces, the mechanism is lossless. So there is no friction between the components regardless of how long the simulation runs. Okay? So before we jump out of the simulation run environment here, I actually want to come up here and let's look at the output grapher. Okay, this output grapher is the means to examine a variety of results from this simulation. A few things you can do after running a simulation in this output grapher is you can change reference frames to view results in various coordinate systems, display curve results. We can save the simulation results for later review and comparison, and also display results in terms of time or other criteria. Okay. So you'll notice, just to talk about this output graph for just a little bit, it's divided into different sections. We got the browser, we got the graph, and we got time steps. Okay. Commands specific to the output grapher are located up here at the top across this toolbar. Okay. So the first thing that I want to do is I want to come over here in my browser, and we're going to, let's look at maybe some of our standard joints in here. All right, specifically on this Revolution 2. Okay, so notice here, I'm going to expand this out, and then notice for that Revolution 2, we got different folders in here. So what I wanted to look at is actually the driving force. So I'm going to check this node here, and we're going to see this force actually displayed in our output grapher. Okay, down here at the bottom, this prismatic joint that it added, I want to also come in here and let's look at maybe some velocities. Okay, so here you'll notice we get some time variations here, and then we also see it down here at the bottom. So it's just a nice way to get some data out of our simulation to see what's actually going on. So you'll notice here that we did some velocities and also a driving force, just so we could see and maybe do some comparisons. So one thing that I do want to point out is you can also export load conditions at any simulation motion state to stress analysis. And then in stress analysis, you can see from a structural point of view how parts respond to dynamic loads at any point in the assembly's range of motion. So hopefully, with what I've shown you so far, it'll make you want to go, and if you have simulation in your Inventor, you can go and give it a try and work on some of your components or assemblies. And with that being said, I'm going to turn it back over to Patrick.
Thank you, Jason. As it was going through, if you had any questions, if you want to punch them in under the question portion, feel free to do that. All right, it looks like it was pretty straightforward. If you haven't already, search Live Lab Learning on Facebook and like our page to receive the latest information and special offers. When you visit our website, livelablearning.com, there's a complete schedule of upcoming training and future information on webinars. Thank you for joining us today. We hope you found this webinar informational and it helps your business. We look forward to you joining us on our next webinar on the 12th, Simulation with an Inventor Professional Frame Analysis. Other than that, you guys have a great day, and we will see you on the 12th. Thank you.